Deterministic side effects. There is a dose threshold for these side effects. They are dose-dependent side effects, and there will be a dose-related severity. Examples are cataract, infertility, and alopecia. Stochastic side effects. These are dose-independent side effects. Probability of these can be increased or decreased but not completely removed. Examples are cancer, teratogenicity, and genetic side effects.
It was recognized early on that radiation has harmful effects. Recommendations for radiation protection were published already in the late 1920s by the International Commission on Radiation Protection, ICRP. The three ground principles are: all exposures must be justified. All doses should be kept as low as possible within reasonable limits. Dose limits were created acting as upper limits of radiation doses which humans may be exposed to. These limits would not apply to medical exposures and the natural radiation we are exposed to.
LARA, which stands for as low as reasonably achievable, is a radiation measure for minimizing radiation exposure. 3 safety measures include time, which is minimizing the amount of radiation exposure time; shielding, use protective gear such as radiation glasses to protect sensitive organs; and distance, to keep as far away as possible from the source of radiation.
Protecting the employees from radiation is sort of a multi-layered defense in depth approach. We use protective shielding, we use protective clothing, things that will keep the radioactivity either off the person or inside the person. And we have extremely sensitive detection equipment. We have equipment that can detect radiation at minute levels, almost down to the atom. How much employees are allowed to get in a year is regulated by the CNSC. Employees can typically, on average, get 20 millisieverts a year for over 5 years, on average. Our employees typically never get close to that. Most employees that are in the highest areas of radioactivity around a nuclear power station would get roughly the dose equivalent to what an airline pilot would get flying an airplane every year. So airline pilots or air crew and nuclear workers roughly get the same occupational radiation exposure.
This man is manufacturing atomic power, using incredibly delicate mechanical hands to move the radioactive material into position. The television receiver, which is connected to a camera in the atomic oven, gives the technician a close-up view of what he is doing. Behind 3 feet of glass and concrete, the sensitive hands pick up a radioactive pellet barely big enough to see. The pellet is dropped into a capsule for storing and shipping. Here the unerring hands, as precise as those of the technician, break off and thread a strip of wire. Another example of progress in working with atoms for peace.
As a first responder, you are probably accustomed to using detection equipment to help better quantify hazardous materials at an incident scene. If you suspect radioactive materials may be involved at an incident, radiological survey instruments can help you quantify the radiological hazard. As with other types of monitoring equipment, it is important that you are properly trained on how to use your radiological survey instrumentation. These instruments have the ability to measure either radiation exposure or detect contamination. The probe can be changed depending on the situation and what you are trying to detect. Many of these instruments are sensitive, and the actual amount of material may be very small, thus posing no significant danger to anyone. At an incident scene, it is important that you select the correct type of instrument to assess radiation exposure levels present and to check for radioactive contamination. Contamination survey instruments usually read out in counts per minute, or CPM, and are used to detect the presence of radioactive material. There are a variety of contamination probes available, and not all probes are alike. Some detectors are designed specifically to detect only certain types of radiation. For example, the detector shown here is designed specifically to detect alpha radiation, but it cannot detect beta or gamma radiation.
This is Technician Andrea. In this video, she will demonstrate how to use a standard Ludlum survey meter, also known as a Geiger counter. Since Andrea will be working with radioactive material, she puts on her lab coat with a radiation monitoring badge attached. First, let's look at the control panel. Starting at the top left, the first switch is the audio on-off switch. It is better to leave the audio on in most situations, as you can keep an eye on your probe and use the sound to isolate the source of radiation. Turning the audio off can be useful if using the meter around patients, so as not to alarm them. Next, we have the fast-slow toggle switch. This does not mean that you can survey an area quickly or slowly. It is simply to adjust the rate at which the needle reacts to the signal from the detector. On fast, the needle responds quickly. On slow, the needle does not respond as quickly, but gives a more accurate reading. Notice that as soon as she turns the meter on, it begins to beep. This is naturally occurring background radiation, which can be anywhere from 0.02 to 0.05 milliroentgen per hour. Next, we have the reset button, which will reset the needle back to the 0 mark. This is useful when transitioning from a lower to a higher scale. Finally, we have the scale adjustment and on-off switch. In the first position, the meter is off. The second position displays the battery charge. The needle should be in the area that is marked BAT test to show that the meter has an adequate power supply. If it is not in that area, the batteries must be changed. This can be done by opening the latch on the face of the survey meter and replacing the batteries inside. It is important to check the battery every time you turn the meter on. Next, notice the markings next to the knob that display 0.1, 1, and 10. These are the scale multipliers. For instance, at times 0.1, the top scale reads between 0 and 0.5 milliroentgen per hour. At times 1, the scale reads from 0 to 5 milliroentgen per hour. Finally, at times 10, the scale reads from 0 to 50 milliroentgen per hour. Note that when you use the times 10 setting, you must use the scale that reads times 10 only on the left. For instance, Andrea detects some radiation and has to switch to the times 10 multiplier. She uses the bottom scale and finds that she is getting a reading of 13 milliroentgen per hour. If she had used the top scale, she may have believed the exposure to be 17 milliroentgen per hour. This is a common mistake, so be sure to use the correct scale. Next, let's move over to the Geiger-Müller tube. This instrument can only pick up ionizing forms of radiation, such as alpha particles, beta particles, gamma rays, and X-rays. The meter will not pick up microwaves or infrared radiation. The thin mica window in the front can detect all 4 types of radiation. The sides of the tube can be used for detecting only gamma and X-rays. Watch as the beta particles from this carbon-14 are easily detected through the front window, but cannot make it through the sides of the tube. Now as Andrea moves over the cesium-137, notice that the probe picks up the gamma rays through its side. Some forms of ionizing radiation also cannot be measured with these meters. The low-energy beta particles that are emitted by tritium are not powerful enough to get through the thin mica window on the GM tube. So tritium must be measured with more sensitive instruments, such as a liquid scintillation counter. Finally, an important law to remember while surveying radiation is the inverse square law. In a nutshell, the inverse square law states that if you double your distance from a source, the radiation will be at 1/4 of the original distance. Let's say Andrea finds a more powerful source of radiation. It maxes out the times 0.1 setting, so she turns the meter to the times 1 setting and hits the reset button. Seeing that that is maxed out as well, she switches to the times 10 setting and reads from the times 10 scale to find her reading. When she is finished, she is sure to turn the meter off for storage.